Hello, my name is Daniel Perez. I will be presenting the FPGA system that I've created for the ECE 178 course end of semester project. The goal of the project was to create a system and a program that could display a message on the LCD, read in keyboard inputs, store data to an SD card, read data from an SD card, and read a push button input. So the system was generated in SOPC Builder. It was then the pin assignments were made and the system was compiled in Quartus 2 version 12.1. The FPGA board was the Altera DE2, and that was interfaced with the computer using the Altera monitor program, where the assembly program was compiled and run. The IP cores used in the system were the Neos 2 processor, the on-chip memory, SDRAM controller, the SD card interface, the JTAG UART, the LCD controller, the I/O for the push button, and the phase lock loop control. Now a little bit of detail about each core. The Neos 2S is the standard CPU configuration. It is a 32-bit RISC-based processor with instruction cache, branch prediction, hardware multiply and divide, which includes 2 M4Ks of memory, and can function at up to 42 DMIPS at 85 MHz. The memory modules used were the on-chip memory, which has fast access time, dual port access capability for 2 masters to access the memory. The SDRAM controller was set at a capacity of 8 megabytes and can be specified for data width, address width, and architecture. The phase lock loop control, or the PLL, was necessary for the SDRAM to correctly function with the system, and the PLL outputs a skewed phase clock input to the SDRAM. The SD card interface was already built into the DET board, but the SDRAM card must be formatted to the FAT16 format and be less than 2 gigabytes of capacity. The SD card memory is divided into clusters of 4K with a buffer size of 512 bytes, and also includes multiple registers for data, instruction, and status information. The JTAG UART is a communications interface between the host PC and the FPGA system, which communicates via serial connection. The JTAG UART uses 2 registers, the data register and the control register. The data register was used in the program to hold the ASCII values from the keyboard, and the RValid bit verifies that the data is valid. The control register holds bit information for the interrupt functionality of the JTAG. The parallel I/O cores can control up to 32 I/O ports. The I/O core used controls 4 ports for the push button inputs in this particular system. Each core has memory map data, direction, interrupt mask, and edge capture register. The LCD display is a 16:2 character display. It was already integrated with the Altera DE2 board. It uses 2 8-bit registers, the instruction register and the data register. The data register simply holds the ASCII values to be displayed on the LCD, while the instruction register can hold information for where the character will be displayed on the LCD, as well as cursor information, and can clear the entire LCD display. So these are all the cores added to the SOPC Builder application. You can see the base addresses listed to the right of each core, as well as at the top the clock input of clock 0 going into the PLL, and the PLL outputting the system clock and the DRAM clock, which has a phase shift of 3 nanoseconds. So once the system was generated in SOPC Builder, the system block was inserted into the schematic in Quartus 2. From there, the pins were assigned, and the physical pin locations were set in Pin Planner, which is an application based in Quartus 2. Once complete, the system was then compiled, where the Altera monitor program was used to interface the system with the computer and run the assembly program. The program used will start off by defining the base addresses for the I/O cores. The enter text is displayed on the LCD. The program then enters a loop which reads from the JTAG data register from the keyboard data that was written to the JTAG. When each ASCII value is read, it is then written to the SD card. The program remains in that loop until the enter key is pressed. The program then enters another loop which waits for a push button to be depressed. Once that push button has been depressed, the SD card data is read and displayed onto the LCD screen. The program then jumps to another loop which pulls a second push button, which is a restart, that takes the program back to the enter text initialization, where more keyboard inputs can be read in from the JTAG. So now we have the demonstration of the system and the program functioning. So at the start of the program, the enter text is displayed on the LCD. In the terminal, keyboard inputs are entered, and then once enter is pressed, the push button is pressed where the data is read from the SD card to the LCD. The reset button is pressed and more data can be entered. So that concludes this presentation. Thank you for your time.